Welcome to the video on the electromagnetic spectrum. This poster, which is usually hanging on my wall over on the left-hand side, is a poster of the electromagnetic spectrum. This represents all the different kinds of light waves that are available, and the sun emits pretty much all of these waves. So on the electromagnetic spectrum, the waves are broken down by wavelength, which also correlates to frequency, as you saw in the last video. The shortest wavelengths are the ones on this end of the scale, and that would be something like gamma rays, and these guys are down to the picometers, if you remember your metric unit conversion list. The largest waves are the sonic waves, and they're all the way at the other end of the electromagnetic spectrum, but all of these count as light waves. They are different from sound waves, which are something completely different. But all light waves, they travel at the same speed, they have different wavelengths, and they have different properties. Now, what we usually think of as light is called visible light. And visible light can be, it comes out of the sun as white. It can be broken by a prism, such as this one, into the rainbow that we're familiar with. So if you guys know the Pink Floyd t-shirt that had the prism with the light, that's what it's all about. The all the electromagnetic spectrum, the visible light occupies only this tiny little region here. So of all the light possibilities out there, our eyeballs are only capable of seeing a small fraction of the possible light waves. And then that is even broken down into everything from purple to red, purple being the most energetic, meaning it has the shortest wavelengths, red being the least energetic, meaning it has the longest wavelengths. Wavelength for purple is about 350 nanometers, and the darkest red is about 750 nanometers. Okay, so let's talk about each of these different kinds of waves and break them into categories. So the longest waves, the radio waves, so these things are huge. Some of them can be several meters long. If that's the case, you have to have an antenna that's also several meters long. And they have these antennas sort of buried underground, these giant antennas to catch these radio waves. And so these things can carry signals over light years. When we beam messages into space, we're using radio waves. And those giant telescopes, not telescopes, but those satellite dishes that SETI has looking for extraterrestrial intelligence, they're trying to pick up radio waves from other places. We can find radio waves from extremely distant stars on the other side of the universe and looking at those. Radar waves are a little bit shorter than that. They are used for echolocation, so like bats and dolphins, and then we've also used them for ours when you have that screen and the thing going around and goes beep, beep, and it's trying to find something. That's echolocation. In order to use echolocation, your object has to be larger than the wave. So if you have a bat, and this is our bat with little ears and bat wings, okay, very Halloween. So this bat is sending out a wave like this with that kind of amplitude and that kind of wavelength. While you have a tree here, the bat's going to know the tree is there. But if you have a tiny little bug here, if the bug does not actually get hit by the wave, then the bat doesn't know the bug is there. So the wave hits the tree and then bounces back from the tree and hits the bat, and then the bat knows that there's something there. And so echolocation is only good for things that are large in the wave, which is useful why we can use them for aerospace, because when you are the control tower for an airport, you don't want to know where all the birds are flying. You just want to know where the airplanes are flying. So you use a wave that is bigger than a bird, but smaller than an airplane, and therefore the airplanes will show up on your radar screen, but the birds will not. Okay, microwaves. Everybody has probably used one of these before. Probably even have them in your home. But that is a certain kind of energy, because it's got a certain wavelength, and it is used to energize the water molecules in your food. If you ever wondered why certain foods take longer to heat up than other foods, it has to do with the water content. So the higher the water content, the longer it's going to take to energize all those water molecules and therefore heat it up. Infrared waves are also heat waves. Now these aren't necessarily heat waves, which is why as soon as you turn off the microwave, you can stick your hand in there and it's not hot. But your oven uses infrared waves, meaning that the whole air gets hot and the heat waves travel through the air to heat the food. And when you see a red lamp in your Burger King keeping those nasty sandwiches warm, that's an infrared light. Okay, we already talked about visible light. Again, it's a tiny fraction of light, and like I said, it comes from the sun is white, and you break it into the colors, and that gives us the rainbow. Ultraviolet light, now this is least energy, and going up to most energy, ultraviolet light has more energy than visible light. So it is used in tanning salons, and it's what comes from the sun. It makes us tan, and therefore tanning salons are not any more safe than tanning outside in the sun. X-rays are even more energetic than that. They can ultraviolet light is stopped by your skin. Okay, so you get skin cancer from tanning too much, but you're not going to get lung cancer from tanning too much. X-rays can actually penetrate through your soft tissue. The only thing they can't penetrate is your bones, which is why we use X-rays to take pictures of your bones. So the bones will actually show up in the picture as something that the rays bounce back from. Gamma rays, we talked about that a little bit when we did the nuclear reaction unit. And every time you have a nuclear decay, it emits gamma rays, which are high energy. Do not get hit with gamma rays too often, or bad things can happen to your DNA. And cosmic rays, we don't even experience here on Earth. That's why we call it cosmic rays. They are blocked by our atmosphere, and that's a good thing, because if they weren't, we would be cooked in a few seconds. And this is why when we send up spaceships, we have to cover them with gold. The gold atom is a very large atom, so it can block, hopefully, those rays. And so we cover the spaceship window with gold, and the astronaut's visor is covered with gold, so that when they're facing the sun, then they put the gold down, and that blocks the rays. If they're on the opposite side of the Earth from the sun, then they don't have to worry about it, because then the Earth blocks those cosmic rays. So anything that is more energetic than visible light, okay, our body's pretty much designed for visible light. Anything more energetic than that can cause cancer. Now, how likely it is to cause cancer has to do with how energetic it is. Cosmic rays, like I said, will cook you in a couple of seconds. So it's not even going to really cause cancer, but it can kill you because it damages you too fast for cancer to be an issue. These, it's not going to kill you anytime soon, but it could cause damage in your cells of your skin, which can accumulate over time and cause cancer. So these are the different kinds of light waves on the electromagnetic spectrum that you need to know for chemistry.